Hi, everybody. Thanks for joining me today for Time History in RISA. This webinar here, as it mentions, that we're going to be going through the new feature to version 14 of Time History, and we added that recently. My last webinar was on dynamics, so this is a kind of a perfect lead-in to the Time History feature here. If you did not get a chance to watch the dynamics webinar, I do suggest you take the time and go back. It's on our YouTube page. So kind of starting off here, we'll go, switch slides here, just with a quick definition of what time history is. So a time history analysis uses the mass, stiffness, and damping matrices to solve for the force vibration of the structure due to an implied load that varies with time. So time being the main point there, but it is important to mention that we are doing a mass, stiffness, and damping matrices. So we're actually adjusting the matrix based on different elements there. As they vary over time. So kind of simple is to think about it that way, but as you can see, it'll get pretty complex as we keep going. So we've got some examples that we're going to be talking about today are going to be two types of examples. One is going to be a dynamic equipment example. So an example of that would be maybe a turbine. And what this is, the idea with a dynamic equipment is that you've got a heavy equipment that will be focusing on this displacement. We're going to be looking at the equipment because the equipment operates at a resonant frequency. So we want to make sure that that is not close to the frequency of the structure, so that with the equipment doesn't have malfunction, but also so that the equipment doesn't have effect on the structure in any way. So we can also think about reciprocating compressors. These are also types of dynamic equipment. And then smaller type of equipment, like an MRI machine. And that one would maybe focus on the velocity to ensure that the VMR machine was working properly as the structure responds to it. So there's that type of example. And the main point with these types of examples is that we'll be applying the load to a node or joint. We won't be applying to all nodes. In a building structure, you're really thinking a little bit more differently for things like seismic time history. In that case, that will happen to all the nodes at all the time, at the entire time. So that will be focusing on total joints or total amount of nodes in the structure. And when we look at the seismic analysis of the structure, we're going to focus on, does the code check work? Do the detail reports work? Where when we're looking at dynamic equipment, we might be looking more at deflections and displacements and things like that. The other type of example in the building would be a blast loading type of example. So I'm going to show you kind of different pieces of this with different examples. We'll focus really in the program so we can see how to use it. So kind of talking about how to use it, it's really easy to apply the time history. There's just some basic steps that we're going to go through, and let me just outline them now. And then we'll go through these steps one by one. So first thing you want to do is define a time history pattern. We have some predefined patterns in the program. So we tried to put some things in there so you didn't have just a blank slate. You have some examples, but also maybe we have earthquakes that are historical earthquakes that you might want to use. But then we also have some quick examples in there for you too. And then once we define the pattern, we'll want to apply those to as loads to the structure. So I mentioned that you're going to apply them as an individual load to a joint, or you're going to apply to all joints. So that's the two types of ways you'd go about doing the loading. And then once we've done that, applied the loads, we're going to create load combinations to use these time history loads. They're a new type of load. So you have, just like any other type of load, dead load, live load, we're going to have a time history load. It's going to be addition into the load combination generator there. And then for the next step we're going to need to find the natural frequency or fundamental period of the structure. So this is the one that I would mention that you should watch the dynamic analysis webinar that I put on, but that one is pretty easy. We're just going to go through the real basics of trying to find the mode shape of the structure. And then the last final piece here is to run the analysis and review the results. We've got a great tools to find the analysis information. We've got some new features that we worked in there to help us really aid in this feature. So I'll be showing all of that. So let's jump into the program. So I'm going to kind of jump into RISA 3D to start. Now, let's see here. So RISA 3D, actually, I opened up an existing model. I'm going to just delete all of my results and anything. And in this model, all this is really is just a, actually, I'm going to turn it into a moment frame. So all you'll notice here is just, this is just a moment frame. It's a tube shape, just so we see. I've defined some basic load cases, some self-weight with y -1 for gravity, and I just put a distributed load just to account for maybe some of the tributary dead load or self-weight of the structure that is accounted to this beam up here. But there is already some self-weight for the actual members themselves. That's all that's in this model. You'll see the load combinations and just have dead load with a factor of 1. So nothing in the model so far. What we're going to do here is we're going to create a time history function starting out. So to do that, you'll see that there's a little icon that's next to the dynamic icon says Edit Time History Function Library. You can also go to Modify, and you'll see at the bottom there it says Time History Function Library. You click that. And inside there, you have a laundry list of different ones. I may have a little more than what comes out by default here, but we have a lot in here to start with. So you can take a look around. Let's just open one just to review what this means. So I'm going to say here, we can either generate one, which we will in a second, but I'm going to view edit just so we kind of know what we're looking at. So when I view edit, it opens up an existing one, and it allows me to make changes to it or just take a look. And first thing I can see is it just kind of looks like it's very densely packed in here. So this display range helps me to just target like a plot option. So just looking for a small range. So I'm going to go from 0 to 1 second and just kind of say apply, and I can see that a little bit clearer. So that was 10 seconds in total for this whole time history pattern, but I'm going to just look at from 0 to 1 second. I didn't actually shorten it. All I did was just change my plot options so I can see the actual pattern better. And what you'll notice, this is time, and then it's going to be plotted over a unitless number here on the left. So we'll determine here what this is when we apply the load. This is a sine function, or you can do sine or cosine here from this tool here. So there's a couple ways to add, and I will show you how to add a specific. If you have one that's not a sine or a cosine and you have very different functions, you can add those directly into the program in a different way. But we'll be talking about sine cosine ones right now. So this is a duration of 10 seconds. It has a scale factor. You can adjust that. The phase, right now it's starting at 0 degrees. And you can input either the frequency or period based on the hertz, the RPMs, or seconds. This one is at 30 hertz. You can ramp up and coast down, and we'll do that in my model here that we built. But I just wanted to show you what we're looking at before we build. You can also print this. So if you print this, it'll print out a picture of that function there. You can export it. When you export it, you'll get the values and all that into a data for you, so you can actually see what's going on. And the data and the values here, if you scroll down, what you're looking at here is steps, and then over time, and then the value. So I'm going to say cancel on that. And let's create our own for a second here. So just to say generate, and I'm going to give it a name. So we'll call it webinar sine, and I'm going to leave it as sine with a duration, and the duration I'm going to say is going to be 5 seconds, and the scale factor, I'll give that a 1. If you just leave these blank here, this will default to 1, and this will be defaulted to 0. You don't actually need to enter it in. You can tell the program to complete the last cycle, just finishes off. I'm going to use RPMs, and I'm going to say 2400. When I say apply, you'll see I get 5 seconds worth of sine curve going through here. It's pretty tight. So if you wanted to really verify that, maybe you go in a little closer, maybe 0 to, let's say, 3 seconds, just so you can see. You can even narrow it down to 1 second just to see that that's happening there. I'm going to go back to 5 seconds just so we see. Now, the ramp up and coast down, let's apply that so we understand what that is. So typically, if you're in a piece of equipment, it doesn't just start and all of a sudden hit its full speed here. So what we're going to do is we're going to say it takes about 2 seconds for that to actually warm up and get to its full frequency here. And the frequency is going to start at 0. I'm going to say it's going to be the frequency function. In order to start from 0 to get to its full, it's going to be linear, and you can say apply there. And then it's going to actually go not exactly like this. This is showing us as if it's going to be the frequency just starts and slowly gets to that. But let's actually think that the magnitude is going to vary also. You can change that so that it goes to either quadratic. If you use the AutoCalc function, that will vary with the square of the function of frequency. So you can use that as well, but it's up to you. You can kind of see what that looks like here. If we use AutoCalc, you'll see it changes a little bit differently, but let's do linear. So same type of thing for the coast down. So maybe as the piece of equipment shuts down, it doesn't just stop. There's sort of a coasting effect of that. So the same thing we'll do on the back end. So for 2 seconds, and this is just so you see, this is a 2 seconds out of my full 5-second duration here. So 5 seconds in total, I didn't get 2 seconds and then another 5. So you want to build that in properly. And then we'll get to a final frequency of 0, and we'll do this again linear in both ways and apply that. So really my function's only being applied here in full from 2 to 3 seconds, and then it's being turned off. So it's really only running for 1 second at full. So I've got all that in place, and I can just say, okay. Now I have a webinar sign listed at the bottom. In order to create another one, it would be kind of a pain to do that. So what's nice is you can just say create copy, and I'm going to copy this one, and then I'm going to go edit it. So I can just take all what I just did, just change here. We can all see it's webinar sign 2, and this one I'm going to change from a sine to a cosine. And so it'll just be slightly off from what they're here. So we're just out of phase with the sine one. So we have cosine and sine, and we're seeing that it's going to be applied directly to the structure here, but just out of phase. So you've got that all listed in here. Everything looks the same. So I don't have to change all that. I'm just going to say save. And now I can apply those webinar sign and webinar sign 2. Okay, now let's apply this to the structure. So push close and let's take a look. Now I'm going to just get this off of render, and I'm going to turn off my loads just so we understand what's happening. I want to apply it to right here in the middle of my beam. So for example, this piece of equipment is just oddly sitting right in the middle of my frame, but let's just say it applies to N5 only. So in order to do that, I go into the time history loads on the data entry toolbar. You'll see under moving loads, right between load combinations, there's a time history loads. That's a new one right there. If you click on that, and then you click on the actual time history loads, there says no data, but when I click on it, it expands and starts creating some data for me. It starts with 2 lines, so it's just a little different than a normal spreadsheet. So you can apply different loads here. If you just say insert new loading point, you can just keep adding new loading points, and you'll see it just keeps adding and adding, all for the same tag or label. For our case here, we're just actually going to use 2. That means so for one time history pattern, we're applying 2 functions. We can change the factors and all sorts in that one pattern, but we don't have to keep applying different ones. So I'm going to go back and delete. I just wanted to show you it starts with 2 lines, and you can add other lines to that. So for ours here, it's just going to start with a tag. That tag is automatically created by the program, but the label is yours to describe whatever you want. So we can call this machine loads, just for our it's just we understand later what we did. The time step is one entry that is auto-calculated for you if you leave it blank, or you can type a number in there. So that's going to be based on the mode shape. So if you leave it blank, it'll auto-calculate it to be 1/10 of the lowest mode with at least 10% mass participation. So that's kind of typical for a seismic loading. If you're using dynamic equipment like ours, you might want to use like 1/20th of the operating period to put that number for the time step. What this really is just an increment. How often are we applying this time step to the structure? So we'll let the program auto-calculate it. That's probably fine for us. You have some options of the type. You can apply it as a force or an acceleration. And if remember, that was unitless. So we're just going to go ahead and say it's a force. And when I go force on both of those, and then I'm going to select the function from the list, ours are at the bottom here. So we're applying both the webinar sign and the webinar sign 2. Now, like I said, you have a choice to say all joints. We're not applying this to all joints. We're actually only applying it to that N5 joint. So I'm going to type N5 right into here. And I'm going to use the X instead of the X direction and the Z direction. I'm going to use the Y direction. So the loading is going to be applied up and down vertically. And then for that first one in the sine curve. And then for the cosine curve, I'm going to use the Z direction. Now, You've got a couple other fields here. Some of these let me tell you about. I'm going to jump to here, this F factor. So the F factor really here is going to be the magnification factor. So you'll remember when we looked at it, that it was just a unitless number. So let's look at that one more time just so we understand. This is just unitless. So for us, we can go ahead and put the force we want to apply to that. And if you look at the bottom right corner here of my screen before it says force equals kips. So if we put a 10 as that force factor, we're applying a magnitude of 10, which is going to be coming out as kips on our structure. If we're using acceleration here, we would see that would be G, gravity there, load. So you've got all of that inside of the force factor. The T factor would be helping you to increase the time step. So you can apply without having to go back and change all your time step information here. You can just use a factor to help adjust that, especially as you have a long list. This one kind of is silly because we only have 2, but if you have a long list, you can make adjustments to the time factor. When you go less than 1, it's going to speed up that, and then when you go greater than 1, it's going to slow down the time step. Okay, I'm going to come back to the other fields here in the coming up models. So now I have my time history loads created called T1. Now I want to create a load combination to use that. So going to the load combinations, I have dead load listed here. I'm just going to push enter, and I'm going to call this time history. And when you go over to the basic load cases, you'll see here that you have a new category. So you can use category codes. We always saw that. You can use basic load case numbers. Now we have a time history load. And that T1 is what's being called up, and I named it machine loads. So I can say, okay, I can also give it a factor here if I needed to scale it down or scale it up from here. I'm going to leave it as 1. And then before I move past that, I do need to run dynamics. So if I try to run this, it says, hey, you forgot to run a dynamic solution. So it'll go right there for me. So I can say, sure, let's go ahead and do that. You pick for all we really need here is the eigensolution. So we don't really worry about the response spectral analysis portion. We're just really worried about the eigensolution, and you can pick the number of modes. The program defaults to 3. I'm giving it a little bit more. I'm just going to give it 10 so we can see it a little more than 3 mode shapes. And you're going to pick the load combination for mass. So that was why I defined that dead load before we even started. So I have the dead load as my mass, and then I say start solution. It runs through dynamic analysis as a small model, so I can see I have almost close to the 90% here participation. So I've got some good mode shapes really for my model. And then I can go ahead and run my time history. So I'm going to say solve, and I'm going to run through all my load combinations. And what's happening on the lower right corner of my screen, you can see that the load step here is pumping through. So it's going up to 1601 as my total, and it's counting all the way up the bit there. So we get up to 1601. It tells me I forgot P delta. That's okay. We'll get past that. And I get all of my load steps. Now what? You've got your time history applied. But in order to understand really your time history, the best thing to do to start is to look at your deflected shape or in an animation view. So we'll go ahead and go into our plot options here, and I'm going to go to deflection. And then I'm going to see the load combination. I'm going to pick that load combination. I can go directly to a static view based on a time step. But before I even know any of that, I had 1,600 time steps. So I had a lot of time steps. I don't really know which one I'm interested in. Let me animate this deflected shape and say, okay. And now I'm looking at an animated shape that I'm going to just speed up for us a little bit. So we see that the program is now doing that ramp up here. It's actually starting up as we started up as a ramp up. So it's slowly increasing, and then it's going to start moving here. Once we got to about 2 seconds, that was where it was really going to be fully applied from 2 to 3 seconds. And right now we're displaying here this is seconds. So it's going all the way up to 5 seconds, and we can see it's up. Where we go, we're really close to that 2 second mark, and we can see we're really animated in there. And then it's going to run down all the way to 2 to 3, and then it's going to start slowing down as we do what we call the coast down. So we have that ability to look at it in seconds or in steps. You can also see with the steps that we talked about. If one is really interesting to you, you can stop it And that one is an interesting one for sure. You can type one in if you knew. So maybe you said, hey, 1200 was the one I was worried about. You can type it in, push enter, it would jump to that. You can step through some slowly. I'm stepping between them using these arrow buttons. So you have the ability to do that as well. You can also push animate again and let it animate. The other thing is really cool in here is called a trace. So if I click the trace button, I can tell the program here I want to put a trace at the bottom of the screen for joint N5. That was the one where we applied it, and I want to see it for the Y direction, and then I want to look at it in the displacement there. So if I say OK, I can see it just started over, and it's going all the way from across here at the bottom. We're seeing this little bit of ramp up. If we want to jump maybe to a faster one, we can go, let's go over to about 1200 again, and we can say play, and we can see it's bouncing through all that. So this trace will help us see all that information. So this is the animated shape here for that. What I also here I'm going to do is just quickly look at the trace. If you don't want to go all the way into the animated shape, you could just trace a joint by clicking on the left side of the screen. There's a trace button, and you can click on that joint, and you'll see the trace right for that joint as well. This works just like we saw earlier, so you can see displacement, velocity, it changes colors for you if you have any acceleration. Sorry, X was not, but Z was a little bit bigger there. So we're seeing all sorts of information. And then the values that are listed there. So when we were looking at this in the animated shape, we didn't get to see the values. So if you wanted to see the values over time, this is the step, and then the values are listed there for you. You can also narrow this down, this display here. So maybe just jump to like a certain range, maybe 2 to 3, where you're interested in the displacement in the Z direction or in the Y direction, things like that. So Z was out of plane, so you can look at X and Z and see the different range of this. This can be printed, so if we print this screen, we're going to see all of the different information. We can export the values listed here for us. I'm going to push close there. The other thing to mention here is when we look at our joint reaction spreadsheet, when we look at any of our joint deflection spreadsheets, what we're looking at is going to be an envelope. What's happening is this is an envelope solution. So we've got an envelope, and what it gives us as information is gives us what the maximums and minimums are happening. It tells us the load combination that governed. So if you have more than one load combination, but the dash number here, this is the time step. So that time step, you can go directly to that time step to find more information. So you're going to see that in all of the results. You're going to get a, instead of just that load combination, you're going to get a time step as well. So it's a lot of information that's being processed. So I'm going to probably stick to smaller models today just so we have a good sense for the time that it takes to run the model. A smaller model will help us for just quick demonstration purposes. So the next model I want to work on here is going to be called the time history blast one. So example, this is actually in your model files examples. So when you install the program, you'll have an examples folder that has models already for you. So this one's a good one to look through. So let's go ahead and take a look. Okay, so this is a frame, just a concrete frame structure, and what we're looking at is thinking that this would be a blast coming off of the structure. So it would be basically on one side of the structure that would be happening. It wouldn't be all of the nodes. It wouldn't be one node. It's not like a piece of equipment that's hitting it, but it's going to be maybe somewhere off the structure, and we're blasting load onto it. And if you think about how that works, so you have to think about how much load would get to each joint. It possibly here we would think about this as tributary area. So, if this has cladding on it, and now you're going to be seeing force. Force would be maybe associated based on how much it's going to see of tributary area per where that joint is located. So if it's an interior joint, it's got this much tributary area. As an exterior joint, it has a little less. And the way we've modeled that is using the time history loads here, the inner joints and the exterior joints. So they're going to have a force on them with the time step listed here. And this, I'll show you here as this function in a second. It's really simple. But each joint has got a load with a direction in the x direction, which is into the structure. And that x direction here has got a factor. So this is instead of just applying the same load on it, this is going to be this magnification factor, which is saying we're applying that magnification of 37.5 to that node. Now let's take a look. I'm going to just pull up the nodes we're looking at. So if I go to my view, I saved a state here for us. I'll retrieve the state with just these members. And let's take a look. So when we look at this here, we have an N17, which is that interior one here. So we're seeing 37.5. So that one's because it's only at the top story, has less than half this load of the N15. And then N13 and 11. So those are going to be adjusted based on their tributary area, and then these exterior joints. So we're applying it to the joints with this F factor. So you see all of that listed there for the F factor listed in in that column there. Let's take a look at the function that we're applying. So in this one, if we look at the function, I open up, it's an existing function called blast loading example, and I can edit it or view it. Now this one is not a sine and not a cosine. This would be one that a user would enter in directly. So I'll show you that at the very end of this presentation. I'll show you how you can enter in your own manual loading here. This is pretty simple. You can see just has a few, it's only 0.7 seconds, has just a few variation points, very large in the very beginning, and then it goes into the negative, very small amount there. And you don't have any way, you're not going to edit this through this portion here. So if you wanted to, you could create this it's a text file is what you're going to import. You can export this information as well. So you can import, export. You can print this as well, like I mentioned. I'll show you a print on another one here, but you can do all that information right from this screen. The other thing I wanted to show you on this is that, so this is got using what we call the runout tab. So if we close this here, I'm going to show you the runout tab. And this is telling the program here that specifically we are going to be allowing the loading to complete. And then after that, we're going to let the structure come back to, using momentum, come back to its steady state or stopped. So as it's running through, we call that the runout. So this blast in particular was only 0.7 seconds. If you remember, we look at this, it's very short. So what we're telling the program to do is to then beyond that go to 2.7 seconds. So it's going to go, the whole thing is going to be 2.7 seconds in total. And the structure will slowly come to a rest or stopped. So we've got, let's see here, I'm going to go into the load combinations, and I'm going to need to run, again, that dynamic solution. So when I try to solve the time history, it's going to go ahead and say, probably can't do that. Let's see, time history. Solve that. It tells me, hey, you forgot the dynamic solution. You can just run the dynamic solution if you want, but it always is, for me, I forget to, and then it tells me. So I have 15 load combinations here. I'm going to say start solution. And what that does here is it goes through and solves all of that. I have 100%. So I have 100% mass participation. And then I can go back and I can solve this load combination with just the time history. It's running through on the bottom right corner, 1,222 different load steps. So we're applying both blasts, which you'll notice too here is we've got an interior and exterior. We define them separately because actually we probably didn't have to, but gotcha. So we were using different load labels. So just for helpful, just so it breaks it up. But actually everything is very consistent between the two. So it could have all been jumped together. But when you do those tags there need to be entered in separately here under the BLCs. So we have two of them, they have the same factors, but this might give you some flexibility. Maybe something else is attached if you wanted to adjust things differently. So once you've got that all run, you can look at the actual model here. We can see that let's look at the deflected shape one more time. So we go into load combinations and start with the animated shape. I'm going to say, okay. And I'm going to scroll all the way across here, and I can see I'm just making it a little faster. And what's happening is here, that's the first blast. Let's go actually into seconds because that's helpful here. So 0.7, that's when the actual structure started, got the blast, and now we're just going through the 2 seconds afterwards. So we're going up to 2.698 seconds. And the trace on this, let's add a trace so we can see that a little bit better. So if you go to N27 possibly as a joint might be helpful to see. We're looking in the X direction displacement. And I can see, so the starting off point is going to be high, and then it's going to be scrolling across and it starts to kind of slow it down. So you can see that it gives you that different piece there. Now, this model here, we close this up. So we can see, we can send, this model is actually a good one to show. We can send this out. Let's go ahead and turn off our nodes, and we can send this one out for a animated shape. What's nice about this is really, like I mentioned, the animated shape is everything. It tells you so much about the model. So it's really important to be able to see this, not just in RISA. So we have an ability to send the animated shape out, so you can export it right to a file and watch it outside the program. So let me go ahead and show you that. Let's pull up examples, and I saved it right out here. So it's called, we had called that time history. And if I open this up, you can open it in any viewer. It's a WMV file, and you can see it's just going to be showing us directly this animated shape. So this is great for presentations. If you have outside of RISA, you could put it, to do anything, but it really helps you understand what is happening in the structure if you can be able to see this. So this is a great feature and newly added into RISA. So we've got that. Let's close that. The other thing I wanted to show you is we can export things too, right out of the program too. So you can click on this export button. So I showed you can push the trace button. When you click on the trace and you can click that, you see this trace information. What you also can do is click on the export button, and this allows you to export different pieces of that. So it's going to be tons of all the information we talked about. There's so much information you've got. You've got displacement, velocity for each joint, for different directions. You can do the things like that. You can send it out for a range. You can send it depending on what you're looking for there. If you want to work with this in Excel, or if you want to look at this in a data file, you can export that. And let's call this a export example. And it just quickly happens there. And then open up that, and we'll just take a quick look. It's not super pretty because it's a lot of data, but it shows you what's all the power of what you can see. You can have narrowed that down. It might be helpful for you to look at certain steps or certain time frames, but it's a lot of information. So that can all be exported as well. The next model here, I just want to quickly show you some information before we jumped into the next one. So that model in particular, I was just working with, I was doing a lot of stuff with damping. So damping for that model would have been important because we were talking about running out. And as we let the model settle, the damping would have been really something that was important in what we were seeing on that model. So inside of your global parameters, you've got a setting called advanced, and then under advanced here, you have the time history section. Right there, you've got the modal, two options. You have modal superposition, or you have the direct integration methods. So modal superposition here is going to, like it says, is by its name, it's defined by the mode shape. So this is a real quick way to tell the program what kind of damping you want to use. Maybe 2% we have listed here. That was my last model. Maybe 5% would be more like a default setting. But this allows you to just click to create one damping percentage based on all your modes for the entire model and all the nodes that you have there. So this does require that you get a sufficient amount of modes to capture the response of the structure to get the given input motion. But you can just do that. That's kind of a quick, easy way to do it, and it's very fast. The other way to do it is using the direct integration method, and that relies on the Hilbert-Hughes-Taylor method. So in that way, you'd have to enter in this alpha value, which is going to be your single integration constant alpha, which varies between 0 and -1/3. So that value here, if you put a negative value, it will tend to damp out or dissipate energy from the high frequencies to help response relative to the time step. So but by default, we leave that at 0. When you have that by default at 0, it's going to be closely matching what we would say here is going to be a little bit more of our default method here. So the other thing here you can do if you want to, if you're going to be using the direct integration method, you would have to define the Rayleigh constant, damping constants. If I open this up here, if you click on that little arrow, you can open it up, and you'll see that it will create you'll have to enter in a mu and a kappa, and those are going to be constants that are going to be multiplied by by the mass damping term, which is going to be the M here, that's capital M, and the kappa is going to be modifying the stiffness, which is the K. So those terms here, what you do is you enter in a target damping that you want to get, and then a frequency range that you're looking to get close to, and then from there it would calculate it for you. So it will calculate automatically for you based on those values. So that's kind of a way to get started if you want to use the damping for either direct integration or the modal superposition. Now, you can also just leave that as something if more of a default value. Let's see, I'm going to go ahead and get out of there, and I'm going to jump back into another model. So beyond that damping, I'm going to talk about the arrival that I had here. So I'm going to open up this arrival example and go ahead. Let's see what I have in here. Okay, so for this example, what we've got is it's just a simple frame I built. But what I have is I'm applying maybe equipment loading on this frame, and it's going to be equipment that hits at different points. Maybe it's like, some kind of a crane rail that goes, the equipment moves across it, and it really starts going across the structure. So the way you can do that is using the arrival. So if you look at the arrivals here, you'll see that you have the ability to say, start that load at, it's a starting point basically. So started at 2 seconds, 4 seconds, 6 seconds. And this function I have in this model is going to be a function that if I open that up, let's see, this one is test1. So really creative name I made. And this is just a simple sine curve. I've got it running for a total of 8 seconds. And so it's going to be starting based on that 8 seconds. So let's take a look, and let's actually increase this so it's a little faster. So let's say it arrives in at 1 second, 2 seconds, and 3 seconds. So in the 8 seconds, we're going to start with N15, then 8 seconds later, 1 second later, another 8 seconds will be applied to the N16, and then a second later beyond that, we'll get N14, and then N13. So it's going to move around. But the best way to see that is actually let's watch it happen on our structure. So say solve current load combination, and it will run. I actually had if you were wondering why I didn't get dynamic expressions, I had a dynamic analysis saved. Dynamic analysis can take a little while if you have a larger structure. So that actually gets saved pretty quickly when you run it. Even if you save your model, just close it down, you'll have a dynamics solution saved with you. It's not really with the traditional saved results like we do other static results. So if you ever open up a model and it doesn't ask you about that, it's probably because you haven't made any change to the geometry of the structure. So it's just remembering all of the dynamic analysis that you did prior. So you could actually, if you wanted to double check that, you could take a look at your mode shapes and your frequencies listed here. They're at the bottom of your results spreadsheet, and you can see that I did already have those saved for my model. So when I've run that time history for this one, I can go ahead and go into the deflected shape, and I can look at the load combination, animate the shape, and say okay. And what I've got here is I'm going to just speed this up just a little bit. So we can see N15 is really feeling that I'm just applying some vertical load in that vertical frequency of that sine curve on there. And then what happens as we scroll, as we go, it goes a little bit longer here. It's going to be going to the first second. Should see that it's going to go, and the second one starts moving, and then the third one starts moving as we get closer. So every second, I'm starting to add that load. So this would help you stage. If there's a way that you're staging to apply these different time histories, that would be how you use the arrival. And this is a really great tool for that. So we can see all of those. If you wanted to, you could trace what's happening in this structure. Let's look at maybe N15 or maybe N10, since N10 is kind of on the path of that. We can look at N10 in the Y direction, and you can see that that's happening there. Okay, so we've got all of that listed here. Let's go ahead and go into a seismic frame example. I'm going to go into File, and I'm going to open up my seismic frame. This is also a model that you have in your examples folder, so if you ever wanted to take a look at it, you can see this right there for you. So this one, if you look at the time history loads, this is going to be based on an earthquake. So this is El Centro earthquake. This one here, I will show you exactly how you would have built this one. This is going to be just after this slide here. I'll show you the slide on how we import this function directly into the program. So this function is definitely different. It's going to be a little bit different than what we saw. So this is 349G. This is going to be an earthquake. It's not even like a sine and cosine. It's not like our blast loading. This is real complex. We're seeing a lot of different loads happen, values happening. These are, so we see that going up and down real fast, and we're looking at 53 seconds for this earthquake to happen. So you can kind of narrow that down if you wanted to see a little closer at what's happening in there, but you can really see it's bouncing all over the place. So this would be one that you'd want to do manually and import it directly. So now I'll show you how to do that. So this is, since I mentioned here, this is an earthquake. It's going to be applied to all joints. It's going to be an acceleration, and its time step there is going to be I listed here as 0.05. I think that's a little small, but the program does give me a little message when it is too small and too big. It won't really hurt my model too much right now, but it is important to note that it will give you that little message saying, hey, you probably want to go and change your time step. You might, for better accuracy. I think it's because I have this one takes a lot longer. We've got a lot of loads applied to it. So I made this a little larger for us, but the program does warn you when you go out of that boundary for the 1/10 of the lowest mode. So we've got the directions listed here, and then I didn't apply any factors. This is all going to be directly inputted from that, since this is direct from the earthquake. So the piece we want to look in here is that we can see if I click on the deflection and I look at the load combinations and the animated shape, we can see a lot of how this structure works. It's really bouncing around. It's got a lot of different shapes going on, and it would be good to see if you wanted to understand a little bit more about the joint deflections, maybe find out exactly one that you'd want to see, because we go all over the place. I'd love to show you here. Let's look at the design results in this one. So we have really high design results. Load combination 5 is what I ran, and it looks like just even in the early load steps, we're seeing some high problems here. So each single one, if we look back to load step, and we're going to go back to step and just go to 6, for example. That was our first one, and push enter. You can see probably having problems in the center here. But you've got the ability to really work with the design results and see exactly which load step was causing any problems. So I would have to size up a lot of these members. Shear is even an issue in some of these models, so I would jump to that. Let's go ahead. And the other piece I really want to show you too is the design results. So if we look at these design results, it's important to see we have a detail report that's been altered for this as well. So let me go ahead. I actually might need to solve this again so we get a really good one. So I will go ahead and solve this load combination one more time. It'll just take a second. I have 1,000 of them, so not that bad. But it's running through 1,000 load steps, and we're going to look at the detail report. And what we've added is an envelope detail report. So it really helps you to see what's happening over all these load steps. You will also create an envelope detail report of load combinations for you, but the load steps really is going to be, since there's 1,000 different applications of load happening during those load steps, you want to make sure that you can pinpoint which ones are the worst case. So using those results to really get to what happened and why it caused any failures. When you also see I use different types of loadings, I just put straight time history in here, but I also combined basic load cases with my time history. You can use your load combination generator to create some of your standard loads and then add your time history into it if you needed. So I just added some gravity and replaced it with an earthquake load type structure for this model. And so we're almost coming on that here. We're about 700 load steps. You'll also notice that, we are applying this to all joints. So it will take a little bit longer when you go to all joints versus just a single joint. When you're just doing a single frame with one joint, it's pretty easy to do. And so that's why we're seeing a lot faster when this becomes a little closer to reality when we're going up to 1,000. On all joints. So we've got that. I'm going to solve this in just one more second. There we go. And I'm going to say OK. And let's go ahead and look at our detail report. So from our design results, because that's really where you, and I think I had sorted that worst case. So sort and absolute max. This is sort of our worst case one. We can open up that detail report. And in the detail report, what we see is we've got a variety of information. First of all, this is on the top says envelope. So it's going to be all that's happening in that model for all those load steps. So deflection, the change here so that you can see, for example, as you scroll across, it tells you the maximum and the minimums that are happening. So in this one, everything seems to be in the minimum range. Let's take a look at maybe we see here this is going to be our bending compression stress, and it tells us from load combination 5, these are the envelope of what's happening across that. You also can see that you've got the load combinations listed here. So from load combination 5, it was load step 6 that caused this worst case. So if this happened all the way across there, let's also look at, let's just renumber these a little bit. And if we look at this one, for example, you might see ones that are a little different. So you can see when the deflection varies, you can see that as load combination varies here, the different time steps, you see a minimum and maximum and what contributed, the contribution for that. So you've got a large amount of information in this detail report that's all brand new. And if this calculation is based on this load step right here. And we can also, again, we can see all the information can be exported directly out from that detail report, from that design results. Just to point out too, it's in every, this is in every single spreadsheet, you're going to see this load step. It's a really powerful tool to see all that. Okay, so now how did we get that BLAST example, the El Centro? How do we get those? Those are really, really difficult, and how do we end up importing that information? So to do that, let's take a look. I'm going to just jump right out of here, and I'm going to go back to my slides. There we go. Okay, so what we did as, for example, you can go on to the website, which is the PEER, or the Pacific Earthquake Engineering Research Center, and that's kind of their website. I just went up there and found it there. It's they have a database of tons of records for different types of earthquakes. So you've got a laundry list of different information on that. So what you're looking at here is just gives us just a snippet of it. And this is actually Newport Beach. So right here in our backyard, the Northridge earthquake in '94. And we've got, what it tells us here is it's going to giving us all this different data. We need to get that into the program. So to do that, you would create a text file very similar to this one here that they give you that format, and you just add a little bit of information. So the top information is just going to be, you know, what do you want to call it? Northridge 90 would be what we'd call it, and that's going to be that listed here. You've got a what's the multiplier? So if you have any multipliers on that, you can do that inside of the text file. Like I said, you also could have just done that right in the F factor, so you can adjust it out in the RESA program as well. The piece of information that comes off of here is the time step. That first piece of information really is that time step, which is going to be in seconds here, 0.01. That's your time step listed in both there. The next piece of information is the record per line. So you see that in both, you have 1, 2, 3, 4, 5 records on there, that point. And here we also have 5 records. So we're just saying records per line. And then the next piece is going to be how many of records. That's how the PEER information comes out, as 5,200 records. And then we have it listed as number of lines. So we're counting, so we basically take that 5,200, divide by 5, and that's that number right there. And then all you have to do is copy all of that data that they give you and paste it right into that file. So you have it all listed in there for you. You can build this from scratch. Like if we were doing that BLAST example, it would be just grab one of these, copy it out, and then put it right inside as like, I think we had maybe 5 or 6 data points, super small. When you're using this much information, 5,200 records, that would be really difficult. So you want to have to, you just be able to copy it right out of that text file. And so it becomes really easy to do from the type of information you're getting out of the databases to put right into an input. So you have a folder inside of your program that's going to be the time history folder. That would be where you store it, and then RESA can find it when you open the program. The only trick is you have to close the program and reopen the program so that you see this new item in here. But you can also find all this information right in the help file as well. So, very important to see how to do it real quick, but I want to make sure that you also see if you go into the help file, it will give you information on how to build this. And the other quick trick is just to copy one we have existing and then just rename it so you can just build off of what we already have going for you so it doesn't take you too much time.